In Unit 10, we'll be talking about the gas laws, which are actually really important when you're talking about the study of matter. Because if you think of a field like this, you might think that if it's an empty field or an empty room, you might think that there is nothing in there. But actually, don't forget that all those empty spaces are always filled with air or some kind of gas. And gases are still made of matter. We don't think of them in the same way as solids and liquids as taking up space, but they actually do. So in this unit, we'll be looking more into how those gases work, how they interact, and how we can apply math to predict their behaviors as well. All right, so in this first section, 10.1, we'll just be setting an introduction, just laying some of the basic information we need to understand so we can make sense of the mathematical gas laws, and then we'll be looking at the first mathematical gas law, which is Boyle's law. So in more detail, we'll be going over the molecular structure of gases. We'll be talking about the kinetic theory and how it can describe gases. We'll define what pressure is, and finally, we'll go into the math examples of Boyle's law. So let's start on square one. Let's answer the question, what are gases? This is a pretty basic question, but let's go ahead and talk about our basic information on this. So we know that gases are one of the four states of matter, right? We know the others to be solid, liquid, and plasma, and that gives us the four states. So, some examples that we're already familiar with is the air that we breathe. You know that you breathe in oxygen and you breathe out carbon dioxide, and those are both gases. Let's see. Carbonated drinks and sodas. I know you usually don't think about this one, but when you drink that liquid soda, actually what's dissolved in it is carbon dioxide gas, and that's what makes it so bubbly, and that's what sometimes gives you gas. And finally, the tire pressure. And if you ever looked at your car or your bicycle, then you know that you're not running around on a solid block of rubber that are your tires. They're actually hollow and they're filled with air. And so it's actually that air that is holding up the entire weight of your car or your bicycle. So it's kind of interesting to think of it in that way. Now, all these gases, we can study them and we can predict how they will behave by using the gas laws, which we'll be seeing more in the later sections. Now, how do they work? What do gases do down at the molecular level? So as you can see from this animated GIF that I have here, the gas particles are always bouncing around off each other. And this is really very different from what they do in the gas state and in the liquid state. So I have that example up here as well, where here I have the solids, and the solid molecules are always very ordered. They hold on to each other very tightly, so there's not a whole lot of movement. And in the liquid particles, they're still very close together, but they're a little bit more fluid. There's a lot more movement between them, and they're not set in place. And so it's all different when it comes to the gas phase, which these gas molecules actually have so much energy that they're always bouncing off each other, and they fly off into every which way, and they're not confined to any one small space. They go all over as far away as they can from each other. All right, so this actually gives us the properties of gases, which is that they don't have a definite shape. They will always take the shape of the container that they are in, because again, the gas molecules are always bouncing in every direction, and so they take up every bit of space that they can. And they have no definite volume. And so when we talk about the volume of a gas, we're referring to the distance between their molecules. And as you can see from this, again, animated GIF, is that these molecules are in constant motion, and sometimes they get close to each other, they get away from each other. And so we can actually control those spaces. If we give the gas a large enough container, then those gas molecules will spread out from each other. Or if we wanted to, we could compress that container, we could make it smaller, and then that way reducing the spaces and the distances between the gas molecules. Next, let's talk about the kinetic theory and how it applies to our gases. So if you remember this from middle school science, and as you'll definitely see next year in physics, is that kinetic energy is just the energy of motion. And when we're talking about that, we're talking about gas molecules at the molecular level. They're always moving around, they're always bouncing off each other. So that's where we get that idea of kinetic energy, that always in motion. So for kinetic theory, let's see. We say that these gas molecules down at the molecular level that we can't see, they're always in constant motion, always colliding off each other and flying in every which way. And the way that we measure that is actually by using temperature. I know they usually don't think of temperature you don't think about it as in terms of motion. It's so usually just how cold or how hot something is. But we actually uh, use temperature as a measure of kinetic energy of molecules. So if we watch this simulation on here, what we have here is a container of gas molecules, and I can go ahead and hit play and see how they start to interact. And we can see that the gas molecules are just moving on their own, right? They're bouncing off each other and they have a certain amount of energy, and I can actually control the temperature that I have in this container. And so if I were to lower down the temperature, you can see how the gas molecules start to slow down. They don't have as much energy and they're not hitting each other as often. Or I can also change the temperature. I can raise the temperature, and you can see that the molecules start to move faster and faster, and they carry more energy with them. And so that's the idea that we have for the temperatures. That it's just a measure of how quickly and with how much force these molecules are moving. And now, when we're talking about the gas laws and the kinetic theory, we assume that we make some assumptions about these gases, and we call them ideal gases. And what this means is that our gas particles are always in constant, random motion. They don't have an agenda, they just kind of do their own thing. All right. Also, we talk about these gas particles as not taking up any space. We just consider them as being points, and so we don't have large molecules and small molecules. We just have molecules that don't really take up any space. And we also say that they are not attracted or repelled to each other. So if any of these molecules have positive or negative charges, we ignore that because that's going to mess with our calculations that we do with all this. And also, finally, that the collisions between our gas particles are elastic. And this means that when they hit each other, there's no loss of energy or momentum. It's only transfer between the two. They change directions, but we're not losing any energy between their collisions. And this is really more of a disclaimer, is that when we talk about these ideal gases, just know that they're not actually real. We're ignoring a lot of properties about these gases in order to simplify this and just make our math a whole lot easier. So this is one of those examples where it's practically correct, but not technically correct. Now, these gas laws, they're very close to what real gases behave like, but we are making assumptions. We're ignoring a few things about our gases. But one time that gases can behave, so that real gases can behave like ideal gases, is two different options. They can either be at a very high temperature and they carry so much energy that they forget about all the other stuff, or when the molecules are very far apart. That means that their interactions between the molecules of a gas are very negligible. So these are the two times that we can assume that real gases are ideal gases. Again, that is at high temperatures and when the molecules are very far apart. Next, let's define pressure. And so in a very technical sense, the definition of pressure is that it is the force per unit of surface area. And now taking it back to the example of filling up your car tires or the tires on your bike, or if you were played with an air compressor, then you might be familiar with this unit of pressure. That's PSI, that is pounds per square inch, and it's a good way to remember what the definition of pressure is. If you remember that pounds and weight is really just the force that gravity has on an object. So in this case, we have a force per unit of surface area, pounds per square inch. So just keep that in mind. I really don't want to complicate it more than that, changing our idea of pounds from weight to force. So we'll leave it at that without making it more complicated. And the reason that it's important to understand this is that gases will exert a pressure on a container, and this comes from the individual gas molecules are always in motion, and sometimes they hit the walls of our containers. Now, when they strike that container, they have, they're carrying energy, they have a force, and so that's that hit gives the container a bit of force, and this is what we can measure as pressure. Now, how is pressure measured? We can't see it. We can't bust out a ruler and see how much pressure we have. So the way that it is done is that it's measured using what is called a barometer. And so this barometer was invented by an Italian scientist named Evangelista Torricelli. And there's actually a very neat video that you can watch on the history of the barometer and how it works. But just the quick version of it is that if you can think of a column of air just on the outside, that's what we call the atmosphere. You know, the Earth is always filled with air up until the edge of the atmosphere. And if you can think of gravity, it's always pulling down on objects, including gas molecules, even though they don't weigh very much. But because there's so many gas molecules in the atmosphere all being pulled down, this is exerting a certain force. And the way that the barometer measures that is that basically we have a little dish of mercury, liquid mercury, and a second tube that is stuck inside of it. And so the idea here is that the force from the atmosphere is actually pushing down onto the liquid mercury, and it's actually pushing it up into the center tube. And then, however much distance the air can push up on the mercury, that's what we take a measure as pressure. All right, so going along with that, we have different units that we can use for pressure. And so, see, one of them is that we just take whatever the force is of our atmosphere at sea level, we count that as 1 atmosphere. Another way to measure that is, using the barometer, we can actually measure it in the millimeters of mercury. This is the amount of mercury that pushes up into the tube of the barometer. And we also have torr, which this is named after Torricelli. And again, it's actually the same thing as millimeters of mercury, because that was the measure that Torricelli used to measure atmospheric pressure. And we also have the pascals and the kilopascals, and this is really more of a physics type of answer. A pascal is actually the amount of newtons per unit of amounts of newtons per square meter. And so again, it's more physics-based answer. We won't be dealing with pascals too much, but just know that it's there. And I know that before I used the example of PSI, but we won't be using it because pounds per square inch isn't part of the metric system. So we'll just be ignoring that one. I think it's just a quick way to remember what pressure is. All right, so I'm telling you that we have all these different units to measure pressure, but it's still measuring the same force. So they can all be related, and we can actually convert between them. So here are the conversion factors for all of these. As I told you before, is that Torricelli used millimeters of mercury to measure atmospheric pressure, and so actually 1 millimeter of mercury is worth the same as 1 torr for our units. So just remember that millimeter of mercury and torr will be worth exactly the same. So you can change between these two names, but the number stays the same. Now, we also have the atmospheres of pressure, and so what we measure on this one is actually 760 torr, or 760 millimeters of mercury, are worth the same as 1 atmosphere of pressure. And then finally, we have the pascals and kilopascals. We can go off the atmosphere and say that if we measure the force of 1 atmosphere, it is the same as 1.013 times 10 to the 5th power Pascal. And again, this is in scientific notation. It gets to be a pretty big number. So to simplify that down a little bit, just have less numbers to work with, we can go up to the kilopascal, and this is 101.35 kilopascals are worth the same as 1 atmosphere. And let's look at a problem where we convert between these two units, and these are just the same conversions that we've been doing for a very long time now. It's just changing the names that we're using. All right, so let's say that we had 1,060 torr, and we wanted to change it to kilopascals. And so the way you start this problem is that you write down your starting amount, 1,060 torr, and you set up a table to make a conversion factor. Now, what's interesting and might be a little bit difficult on this one is that we don't have a conversion factor to go from torr into kilopascals. But notice here that actually we have a conversion factor to go from torr into atmosphere, and we have a different one to go from atmosphere to kilopascals. So if you notice here that they're worth the same amount, it's 1 atmosphere, and so we can just cut out the middleman and go straight from 760 torr. It's really the same as 101.35 kilopascals. So let's set that up. We start with torr on the top left, which means that my new torr of the conversion factor will go to the bottom right. And remember that 760 torr is equivalent is the same as 101.35 kilopascals. So I've set up my table. This way I'll simplify it and say that my torr top to bottom will cancel, and I'm left with 1060 times 101.35 kilopascals, all divided by 760. And you can use a calculator for this, and once you do, you get the result of 141.36 kilopascals. So far, we spent our time defining what temperature and pressure are, and now the only thing left to tell you is that we have a very commonly used amount of temperature and pressure that we call the standard temperature and pressure. And what these are is that the temperature, when it is standard, it is 0 degrees Celsius, and our standard pressure is 1 atmosphere. So if we're setting up experiments and we don't know where to start, what properties to set for our gases, we would just use the standard, which is 0 degrees Celsius and 1 atmosphere of pressure. So for our homework problems, you might be given a statement like this, that the volume of a gas is 50 milliliters when it is at standard temperature and pressure. And so from this sentence, even though there's only one number written, we know 3 pieces of information for our gas. We know that its volume is 50.0 milliliters, and then we know that the temperature will also be 0 degrees Celsius because it's the standard temperature, and the pressure, we have the standard pressure of 1 atmosphere. So it's a very useful way of relaying a lot of more information with just less words, and it's a little bit more efficient to do it that way. Now, with all that finally out of the way, we can finally get into the gas laws and start describing our different amounts of gases that we can have. So the way we can describe gases is by using either their volume, temperature, the pressure, and the number of moles. These are all physical properties that our gases can have, and they can share with others too. Now, what's interesting about all these properties is that they are all connected. If you change one, you will see a change in a different unit or in a different property. And these changes are all described through the gas laws that are really just mathematical expressions that we can use to predict the behaviors and the changes in our gases. So let's look at some of that. Our first example here is the Boyle's law. And an example we'll be seeing is using a syringe to change the size of our containers and see what that does to the pressure inside of it. And I'll leave it at that. I'll let you see more of it when we get to the lab so you can see it in action. So now, Boyle's law is named after the Irish scientist Robert Boyle that worked on all these observations. And so this law can describe the relationship that we have between pressure and volume when our temperature is constant. So when we're dealing with Boyle's law, we just ignore the temperature altogether. We just assume that it will stay the same all the time. And so we only focus on the changes between pressure and volume. Now, what Boyle demonstrates that when we're dealing with these gases is that if you increase the pressure, the volume, the size of that gas will decrease. It will shrink down. Or if you do the opposite, the pressure will decrease and the volume will increase. If you decrease the pressure, the volume will grow larger. And so that's demonstrated over here in this graph. And so what we call this type of relationship is that it is inversely proportional. That means that if you have a high volume in this one, then you will have a very low pressure. And then if that volume changes, if you reduce the volume, then you are increasing the amount of pressure. The formula that we use for Boyle's law, it looks like this, where we have PV is equal to K. And what these variables mean is that P stands for pressure, V is volume, and K is just in constants. So in our case, it will just be a result. But we can actually pair this with two systems of gases. That means that we can have a before and an after for a gas that we can make some change in it. All right, so what that formula looks like when we make a change for it is that we have the P1 and V1, our original pressure and volume multiplied together, are equal to the same amount of our second pressure and volume. So let's actually see what this looks like in action so it makes a little bit more sense. So it's a type of problem that you'll be seeing for Boyle's law. And so it reads that what is the new pressure of 150 milliliters of a gas that is compressed to 50 milliliters when the original pressure was 3.0 atmospheres and the temperature is held constant? And so in this one, that is a clue that the temperature is held constant. We don't need any T in our formulas, so we'll use the formula that is only pressure and volume. And so what you need to do with these problems is just know how to read them and know how to pair your information. What is your original pressure and volume, and then what's the new pressure and volume? What's the before? What's the after? And make sure that the numbers stay together in the right order. So when you read through this, notice that here's the clues. The volume of your gas is compressed to 50 milliliters. That means that you're changing the volume to 50 milliliters. So 50 milliliters will be the final volume, the second volume. And so we know that the original pressure, here it is stated as 3 atmospheres, so I'll save that. Pressure is 1. Pressure 1 is 3.0 atmospheres, and my original volume is 150 milliliters. Remember, because we're taking this 150 milliliters and compressing it to something new. So that means that my pressure 2, well, that's the question that is being asked. What is the new pressure when the gas is 50 milliliters? So that's my second volume. Volume 2 is 50 milliliters. So now, knowing this information, we can take it back to our mathematical formula of P1 times V1 is equal to P2 times V2. There is 4 variables in this one, and we know the values of 3 of them. So all we have to do is solve this expression algebraically for that missing variable. So again, I have all my information written down, and I will just fill in what I know. So I know that my P1 is 3.0 atmospheres. I know that my V1 is 150 milliliters, and that is equal to 50 milliliters for my V2, and my P2 is the unknown. So I will just keep P2 as it is. I don't know what to put in for that. Now from this, just solve mathematically, which 3.0 atmospheres times 150 milliliters, and then I have 50 milliliters on the right side. If I divide both sides by 50 milliliters, that will cancel on the right side, leave my P2 all by itself, and it will stay on the left side. So from this, I can look for my matching units. So milliliters on top and milliliters on the bottom. These will cancel out. So now my final calculation on this is 3.0 atmospheres times 150, all divided by 50. And when you do that into the calculator, you get the result of 9.0 atmospheres. Remember, the atmospheres didn't cancel with anything. And this is the pressure that I am looking for, 9.0 atmospheres. So it's how to set up the problems, and how to solve through them is just a matter of knowing how to read the problem, and what is your initial pressure and volume, and then what's the change that you're looking for. So if you need help, make sure that you let me know, and I'll let you practice up on the rest of the problems before we dive into the next section, where we add temperature to the mix, and we'll be talking about the 2 other gas laws that we need to understand.